So today we have Louis to do our campus lecture. So Louis has been a member of the ATLAS collaboration at CERN since 2014. He received his PhD in 2020 from the University of Montreal, where his thesis was on searching for supersymmetric particles and dark matter at ATLAS with deep learning techniques. Since then, he's been with the ATLAS group at UC Berkeley and Berkeley Lab, with research on three fronts: reconstruction of charged particle trajectories, particle identification using machine learning, and measuring the Higgs couplings to heavy quarks.
Okay, thank you. Okay, good. Yeah, so if you guys want to ask questions while I give the talk, it's fine. Sure. Even on Zoom, I have the list of people here, so if I'll see the hands. So actually, let me check. Let me put up the channel.
Questions on chat.
Yeah, perfect.
Yeah.
So I don't have to look at it. And I'll put the sound up if someone starts to speak. Okay, excellent. Yeah, we're going to talk about Higgs physics. Don't really need to go through the intro because you said most things, but basically I segmented the lecture into three parts. So just introduction to Higgs, how did we discover the Higgs in 2012, and then just what I'm working on. So, okay, Higgs boson. First of all, this is the full standard model of particle physics. I don't know if you guys are in physics.
Yeah.
All three of you are in physics. So you guys know, broadly what this is, right? So on the top, you have the quarks, and on the bottom, the leptons. Those are the fermions. That's all matter is made up of these particles. And then the force carriers, these are the bosons in the middle, right? You have the photon for the electromagnetic force. The weak force, this is the W and the Z. And the strong nuclear force is the gluon. This model, right, it's circular here, which suggests that it's symmetrical. The model is built around, mathematical symmetries, which make the model extremely elegant. The problem is, the second you introduce masses into this model, everything breaks down. It doesn't work, which is kind of a problem, right? Or is it? So yeah, is the lack of mass in this model the problem? It obviously is, because we know the matter as mass, right? And if we talk in terms of fundamental particles, we've known like the electron has the mass since the 19th century. And this has major implications, right? The size of the hydrogen atom depends on the electron mass. So this basically sets the energy levels you need to make chemical reactions. So the implications of the exact mass of the electron are huge. And then for forces, there's also implications, right? Of course, we know photons are massless. Turns out gluons are also consistent with being massless, but computations involving the weak forces, they just don't work if those bosons don't have mass. And for example, this has a dramatic implication because fusion reactions that power the sun, they depend on those reactions being explained by the W boson, at least a lot of them. So that's extremely important. That's, needs to be accounted for. So of course, this being a lecture about Higgs, the solution to that is to introduce Higgs boson at the center of the model. And the way this works, I don't want to go into the theory really much, but you introduce this potential here. You guys have probably seen this before. This is the so-called Mexican hat Higgs potential. It's fully symmetrical, right? Which suggests that this can fit into our symmetric model. But since the minimum of the potential is not at the center, this breaks the symmetry, and this turns out that this is the ingredient you need to create particle masses. We're gonna see just a little bit more about that in a second. So we call this the Higgs mechanism, but Peter Higgs famously insisted on calling it the Anderson-Brout, Engler-Guralnik-Hagen-Higgs Kibble and Tooth mechanism, because these are all like kind of the pioneers that it's within a few years in the early 60s, they've all done work that was like strongly overlapping, and have all, they and their team have put together a piece of the puzzle for this.
Is there a way to pronounce that acronym?
However you want to try it. Usually we just call it the Higgs mechanism, but I think Peter Higgs is famously hated that this was like the particles known as the Higgs boson and the Higgs mechanism. But yeah, yes.
Just to understand, in the initial slides, you were trying to say that the particle mass is important.
Yeah.
And why was I supposed to get away with like the first 10 minutes? Sorry, I
What's up?
couldn't understand.
Yeah, the masses, we know that the particles in the world have mass, right? But if we have a model, like the best model that we have, if the Higgs boson doesn't exist, we don't know a way to make that work with masses.
What is the Higgs boson? Sorry.
Yeah. The Higgs boson, it's basically it's another particle, and every particle in the standard model, it's expressed in a framework that's known as quantum field theory. I really don't want to go into quantum field theory, but the name suggests that what is fundamental is a field, right? Like the electric field is a field, temperature is a field. So every particle is associated to a field, and there can be waves in a field. And in quantum field theory, a wave is associated to a particle. Now, most of the fields that are generated by potentials are zero in space, right? Like if you're in outer space, far away from everything, you won't find like an electric field there. But it turns out the Higgs, since the field potential has this weird shape, since the ground state is here and it's not at zero, right? So if you try to measure the Higgs field anywhere in like outer space, it's not going to be zero.
Oh, like the field itself always looks.
It's going to live right there. Yeah, it's going to live in the trough.
Thank you.
And that's the ingredient, right? The model, this works well with the symmetrical model because if you put the symmetry axis at zero, it's fine, everything works. But in reality, just because in nature always wants to minimize the potential. So the ground state is not at zero. And in a couple slides, you'll see what that does.
Thank you.
No problem. Well, in this slide, actually, yeah. Okay. Higgs, since the Higgs field is non-zero in space, as we were talking about. And I also said that excitations in the field correspond to particles, right? So for the Higgs field, this means if like the field is excited, like in this potential, this corresponds to a Higgs boson. It's a particle that you can measure. We're going to see in a few slides how we were able to find that. But one of the other consequences is that fermions, like quarks and leptons, like electrons and quarks and so on, they constantly interact with the Higgs field. That's just like a diamagnetic way of seeing. You have like, this could be an electron and it's traveling in space and then interacts with the Higgs boson and just goes the other way. This sort of like, by analogy, this creates a drag, right? And which creates inertia, which we interpret as mass. But in this model, it's completely dynamic. It's not like an intrinsic property of the particle. And the analogy we always say is that if you have a room full of people, like let's say a room full of physicists and I'm walking through the room, like I'm gonna be able to make my way like very quickly throughout the room. But if like Albert Einstein walks in and everyone's gonna want to talk to him and have interactions with him, so he's gonna move very, very slowly. And that's inertia, that's mass. And that's how this shows up in the model. So there's nowhere if you write the equations, there's like, the mass term is really related to this interaction. I'm trying to simplify as much as possible. If it's not clear, please ask more questions. Okay. So now we've determined that fermions get their mass from this mechanism. So let's look what this means for like nucleons. For example, the proton. The world is mostly made up of like protons, neutrons, and electrons, right? So let's look at the proton. Proton is made up of 2 up quarks and 1 down quark. And we know approximately the light quark masses from a number of sources, and they're like very light. These units, I don't know if you guys are familiar with electron volts, but it's a measure of energy. E equals mc squared, so it's also a measure of mass. Anyways, doesn't really matter, but you see the up quark gets mass about 2 MeV, the down quark is about 4. But if you measure the mass of the proton, it's 908 MeV, right? And if you take what, 2 times 2 plus 4, you're like very, very short. So does the theory just not work? Like, is this like Higgs mechanism is incorrect? I don't know. Well, it turns out this was really too simplified. This is a real problem, okay? Proton is a very, very dynamical object. And if we take the analogy with an electron, like the two up quarks and the down quark, these are just like the valence quarks. Like if you were to measure the quark content of the proton, that's, in most cases, that's what you would find, but most of the energy is actually kinetic in nature because those quarks are bound together by the strong force, which has a very strange property that if things are very close together, they don't feel the strong force very strongly. It's like extremely weak. But as they're like pulled apart, it's like a spring, which is why we draw the gluons like this. It's like a spring. If they get like further apart, then they start like feeling the strong force extremely strong, which pulls them together. And this means that since they're like kind of free to move around within the proton, since energy equals mc squared, energy is mass, most of the mass that are in the protons doesn't come from the Higgs. It comes from, the strong force interactions through the strong force. Yes.
Is that a way of showing like the probability distribution of the quarks inside the proton, or is it like the path they take over time, or what is this sort of?
Yeah, this an analogy for exactly what you suggest, a probability distribution. And in fact, we call this, it's a bit confusing because in jargon, we call this PDF, and it doesn't refer to the file format. It refers to parton distribution function. A parton being either a quark or gluon. And so you have a probability to find either gluons, up quarks, down quarks, but even strange charm, bottom quarks, what have you. This is all inside the proton. Yes.
So the whole circle is a proton.
Yeah.
And the little things are like quarks and.
They're quarks, yeah.
So you said that. So for quarks, you just only stated strong force? Is that like, are you just talking about one force that it interacts with a quark? I don't know.
Yeah. This because the strong force is what it's dominating here, but they're also gonna, like quarks are electrically charged. So they're also gonna interact through electromagnetic forces. Okay, so I always felt like we always talk about the Higgs as this thing that generates mass. But when you look at this picture, it always felt like the rug is kind of pulled under our feet. And it's not the Higgs, but there is a twist. There's a very important twist. Is if you take, for example, the difference in mass between a proton and a neutron, right? So proton, we said it's dominated by two up quarks, one down quark, and the neutron is two down quarks, one up quark. So it would be slightly heavier just based on that. If you take the difference in mass between those two, it turns out that the effects due to the strong interaction almost completely cancel out. And you see that, okay, as you were pointing out, they also interact electromagnetically. This is what it's meant by QED, quantum electrodynamics. But it turns out that the mass difference is mostly dominated by the up and down quark masses, which this is like 100% through the Higgs mechanism. And the implication of that is very far reaching because if the neutron would be lighter, then the proton would be stable. The proton would be stable. The neutron would be stable, and it's, the name says it, it's electrically neutral. So we wouldn't have hydrogen. And, life, if it would even be possible, the universe would be very different. And, we've talked about the size of the hydrogen atom depending on the electron mass, which comes from Higgs, right? So it turns out that it is really fundamental, even if like the mass of a proton is not solely determined by Higgs. The Higgs mechanism is basically responsible for chemistry, biochemistry, and biology if you reduce it to its to the very bottom. Okay, so do you guys have other questions before we move on to the discovery part? All good? Excellent. Okay, so a bit of history. How did we discover the Higgs boson? Right? So I put a picture of the Large Hadron Collider in Geneva. So you guys are probably familiar with this, but it's a huge proton-proton collider, circumference of 27 kilometers. Sits about 100 meters underground, just on the Franco-Swiss border. So you would have Geneva is like down there, and then CERN itself is like somewhere here. And there's 4 main experiments. There's ATLAS and CMS, which are the big general purpose experiments, and you have like 2 smaller, with more target purpose experiments. So ALICE, which is built for heavy ion physics. So right now, while we're speaking, the LHC right now is not colliding proton, it's colliding lead ions. They always do that at the end of the year. So this for ALICE. And then there's LHCb, which is, this is a bit more complicated, but it's B-meson physics. We're not going to talk about that. But I'm a member of ATLAS, right? The ATLAS collaboration. So this is the detector that we're working with. This is a huge detector, right? 46 meters long and with a 25-meter diameter. You see there's at scale 2 people sitting there just to show. When I was making the slides, I was trying to find, like on my phone, I have pictures because I visited the cavern. But they're like super underwhelming because the thing is so huge that the second you're in the cavern, it's like right there in your face. You can't really take a good picture. So that's the best I could come up with. You see the humans for scale here. And yeah, the structure is very modular. So in the center, you have the inner detector. We're gonna see what that means on the next slide. And there's a bunch of magnets, like a solenoidal magnet in the middle, then calorimeters. There's a huge toroidal magnet system, and then the muon detector. Yeah, so this is like a transverse view, right? So from the inside out, you have the tracking detector here. This is just basically like layers of detector, and you're just measuring the trajectory of particles without disturbing them, like as less as you can. Here you have, this is an electromagnetic calorimeter. So particles such as the electrons and the photons will just be completely destroyed here, and you can measure their energy. After that, you have a hadronic calorimeter. That's the same thing, but for hadrons. So for particles that are made up of quarks. If they are destroyed there, we measure their energy. And at the far end, you have like the muons have a property that the rest of the detector is built to like minimize the interaction with muons. So once you like cross the calorimeter, you basically know you have only muons. And so we have a very sophisticated system that can measure the muons very, very precisely. And yeah, there's a huge magnet system to, if a charged particle passes through an electric field, like perpendicular to it, it's gonna bend with a radius that's proportional to its impulsion, so to its speed. And so this way we can measure that. Yes.
I'm assuming that the source of whatever you're shooting out into space is like the circle.
Yeah, right? The beam would be coming like this way.
Yeah, and what exactly, what the electrons or photons are you trying to detect? Is it like, I don't know if that makes sense.
Where the electrons coming from?
Yeah.
Okay.
Yeah, so I'm going to show some diagrams a bit later, but I see there's a bunch of interactions that can happen like very quickly once 2 protons are close together. And then, particle will just like shoot out of it. And then that's how like the Higgs boson, that's maybe a point I should make now. Like it's never going to happen that we're going to produce a Higgs and it's going to like show up in the detector. The Higgs boson has a lifetime that's like, I don't know, I don't remember the exact figure, but it's like created and it decays like extremely quickly. But through the decay products, we can reconstruct what happened. That's the name of the game. And yeah, we're going to see like 3 different ways this happens. So, okay, yeah, I'm talking about like Higgs decay. For example, you can have Higgs can decay to a pair of B quarks, right? It can decay to a pair of W bosons, pair of Z's and so on, a pair of photons. And on this plot here, the y-axis tells you the branching fraction, which is basically if you have a Higgs boson in your hand and you just like count how many times it decays to each of these things, like that's the probability. So you see that the B quark here, that's the most likely thing you're going to see, followed by W, followed by tau, followed by Z, followed by photon, and so forth. So you would think we discovered the Higgs boson with B, right? But it's actually not the case. The main things we were looking for in 2012 were ZZ and WW and gamma gamma. These are not like the most common thing. Well, WW we're going to see. This one is very difficult, but it's also very probable. But ZZ and especially gamma gamma, these are like very small probabilities. So let's talk about why not BB, okay? So we've seen that the proton has like a lot of gluons in it. And it turns out so much so that at the energies we collide the protons at the LHC, like 99.999% of the time, what happens is that two gluons interact together and they just create more gluons. So that's, we call this like QCD background. And it turns out that a lot of time a gluon can decay to a pair of B quarks. And this looks like it can look like a Higgs decaying to B quarks. So since my only handle on finding the Higgs is seeing two B quarks in the detector, right? We can't see the Higgs directly. If I have, two B quarks, do I know it's a Higgs or do I know if it's a gluon? This is very difficult. And at the time, in 2012, we didn't even know the mass of the Higgs. So this made it even more difficult. And another thing, I'll talk about this later, but to see these particles in the detector, that's extremely difficult. And we have like sophisticated algorithms to do that, but they're not like 100% efficient. So at the time, this was just simply too difficult. And this didn't, similar issues for tau leptons. So let's look at ZZ. This one is kind of straightforward, right? You have two gluons and somehow they interact, create a Higgs boson, which decays to two Z bosons, and they both decays to like either pairs of electrons or muons. And it turns out you can, do you guys know what four vectors are, four momentums? Have you done any like special relativity? Right, it's like kind of a generalization of the momentum, right? It's momentum and time, or momentum and energy in that case. But basically, this we can measure in the detector, right? We can measure the form momentum of a lepton. And if we take a vector sum here, we can reconstruct the mass of this thing. And you do this recursively. You do the same thing here, and then you sum up the result. And you should, if this is the only thing that happens, you should be able to see a peak that corresponds to the Higgs mass. And it turns out that this is exactly what you're seeing. The rest in red, this is like other diagrams that look like this, but don't involve the Higgs. And the name of the game here is being able to observe a peak that's not like correlated either with this or this. Here, it turns out we see this kind of clearly, but then if you look like, okay, the colors we're seeing, that was just a simulation, so we can know what to expect. What we actually measured are the black dots. That's from collision data. So you see there's like kind of a little bit of a hint here, right? But not much. So by itself, with this, we couldn't say we found the Higgs. Yes.
I'm not gonna the right Russian answer, like
No
how
problem.
many interactions or how much time or how much data did this?
Yeah, okay.
Yeah.
So this is, let me try to remember. This is not a lot of data. 7 and 8 TeV, this is like 2-3 years. At the very beginning when like the LHC was still like tuning up. So it wasn't producing like that much data. Right now it's producing a lot more. Yeah. Well, at that time,
Okay.
at that time, it wasn't much. Like you can see here, these are really like number of events you can count. So in this bin, there's only like 6. So this is not a lot of statistics. So bi is kind of hard to say. So we need to look at for different things. So what if, for instance, the Higgs goes to 2 W bosons? Now, this is a lot more difficult because W's, they will not decay to a pair of electrons, for instance. It's always going to be like electron and neutrino. Neutrinos are, neutral. They interact like very, very weakly with matter. So in the case of our detector, they just shoot out of the detector and you don't see them. So this is very difficult. However, we know that the beams don't have, or like have negligible energy in the transverse direction when they're crashing into each other. So longitudinally, that's where the energy is. But like away from it, initially there's nothing. So by conservation of energy, if you sum up the energy of all the particles you reconstruct, it should arrive to 0 just by conservation of energy. But since there's particles like neutrinos that you don't see, you're going to see a direction in which you're missing some energy. And just based on that, we can do a fit and like kind of reconstruct a mass. And so you see that the peak here is like really more, like a lot more smeared out. Because since we don't really know where, we are not like guessing where the neutrinos are going, we don't know precisely. It's very imprecise. Yes.
How does this correlate with the density? Like how would I be able to picture this?
Yeah. Well, just because the Mexican hat, if you like have regions of space-time with a lot of energy, like they can be like ripples in the field, right? Along the trough. It's kind of like you're going up the wall like this. And you know, this is in the mathematics, but in the real world, this shows up as a part.
And I'm assuming the vectors coincide with the direction that the
Well, yes and no. In these types of diagrams, this direction is time. Yeah, maybe I should have explained that. This direction is time, so if the arrow is pointing this way, it's an anti-particle, which is why here it's like electron plus, so it's a positron. Because charge is also concerned, right? So here you have a W boson, which is charge. The neutrino is obviously neutral. So this guy needs to have a positive charge. And it's for the other side, it's reverse. Because the same thing holds here. The Higgs is neutral, so by conservation of charge, this needs, if this is positive, this needs to be negative. And yeah, this axis basically just corresponds to like distance between particles, more or less. So yeah, this is very difficult, but you can see that since X decaying to WW happens like a lot more often than to pairs of Z's, this is still helpful. If you see the number of events, right, it's like 10 times more than the other. So everything here that's like solid color, this is like processes that are not Higgs, but they look like Higgs. And then in red, this is what you get when you add the Higgs boson, right? And you see we saw even more events than that, like a little bit of a fluctuation. But you can kind of infer that there's something here that's not only the solid colors. Yes. Oh, it's the same thing. Sometimes, yeah. I'll try to say Higgs boson. Sometimes we say the Higgs, but it means the Higgs boson. Yeah. Okay, and the last ingredient is Higgs going to 2 photons. So this, you remember, this doesn't happen a lot, right, in the detector. Well, the Higgs boson doesn't decay that often to pairs of photons, but it turns out that in ATLAS, like we're extremely efficient at observing photons. Like we can measure their energy extremely precisely, and like we almost never miss a photon if there is one. So this allows us to do this here. You have like other processes that can create pairs of photons. And this is what you would see if you didn't have the Higgs, would just be like the dashed line here. Then when you add the Higgs, you have like that tiny little peak here. But with a very good precision here, you just took like all your expected Higgs event and subtracted by like the computation you've made to estimate the number of background events you would get. So you see here, and this is the mass of this system. And you see you only have like a tiny peak around 125. So that's the third ingredient. Yes. Yeah. Yeah, this bump here. Yeah, this is the same thing because you see on the top, like between the bump, there's like a little dash line. That's our estimations of how much events we're going to get in the detector that have 2 photons but don't involve the Higgs boson. Okay, so away from the peak, it's just completely overlaid with the other ones because we don't expect Higgs bosons there. But just at that point, there's a Higgs at that mass, decaying to 2 photons, so you're just observing like tiny bit more events than you would otherwise get if there was no Higgs, right? But again, like very small bump. But then I just wanted to call out like the power of statistics. So you see here, okay, signal strength, that's basically a ratio of like how much Higgs events we've observed and how many we were expecting, the ratio of those two things. So if we observe exactly the prediction, it should be 1. And if we don't observe any Higgs boson, it would be 0. And so you see here for those different channels, so, okay, well, on the top you have, okay, we've talked about BB and tau tau, and I said these were like, at that time, were too difficult. And you kind of see why, right? You're able to do it, but the answer you get is compatible both with exactly my prediction, and it's also compatible with no Higgs boson. So can't really tell much. The other 3 channels, okay, third from the top, WW, there's gamma gamma, and then ZZ. You see, they are like a lot more compatible with 1, and then you can sort of start to see something interesting there. But the error is also large. But if you combine all of these things, you get a much smaller error. And this is like clearly compatible with 1 and not with 0. And then we can do this in terms of like p-values. You guys know what a p-value is? It's basically just the probability that what you've observed was due to your background that just fluctuated in a way that looks like a Higgs boson, while not really being a Higgs boson. And you can see that like away from 125, that probability is almost 100%. So you would never say you found the Higgs there. Once you get here, right, wow, you're almost at 6 sigma. And this actually corresponds, this is the probability that we've thought we were observing a Higgs boson at 125. But in reality, it was just like all the other processes that, were looking like the Higgs. Very, very small probability. But you would look at like the 3 channels in separation, and it's not really clear that there's a Higgs boson there, right? The signal is very, very small. But since these are like statistically independent analysis, once you look at the data altogether, that's the probability you get. So that's the power of statistics. And that's how we were able to say we found the Higgs. Yeah, it's really just the channels. It's by what Higgs boson decay we're looking at.
So there are 5.
Yeah. Here there's 5, but like there's only 3 that really matter.
And how do you know there's?
Well, you will kind of enforce like, okay, here I'm looking for events that have like, for example, 4 muons, right? Or 4 electrons, or 2 muons, 2 electrons. For Higgs to gamma gamma, I'm looking for events that have 2 photons. So I'm going to just veto everything that has 4 leptons. I'm just going to look at events that have photons. Here I'm going to do the same. I'm just going to say if I see photons, I'm not going to look at that event.
So the one event happening doesn't increase the problem.
No, exactly. So you're basically looking at each event and you're like classifying them into different channels based on what you see. And in this way, the data sets are independent. And so you can statistically combine them at the end to have this very, very strong result. Are there other questions on the discovery? Okay, let's move on. How am I doing on time? Okay, not too bad. This is the last section anyway. I just wanted to talk briefly of like what I'm actually working on. This was all like 2012. I was an undergrad back then. But now, okay, like 15 years later, what are we working on in the Higgs world? I'm not trying to be super complete. I'm just going to talk about what I do. And okay, let's go back to the theory, okay? I said that there's a symmetrical model that doesn't have mass, right? And then you had the Higgs, and that solves everything. So very, very schematically, I put that here, right? Standard model, gauge here, this is the symmetrical part because, okay, these are called gauge symmetries. If you guys don't know what that means, you're lucky, you're going to learn it at some point in an advanced CNM class or something. But okay, that's just for the purpose of today. This is just the symmetric massless part of the model. And then you add the Higgs after that. Very simple. So let's focus right now. Let's forget about Higgs for a sec. So here I'm just in my symmetrical model and I look at my quarks, right? We know there's 3 generations of quarks. It's the same thing for leptons. But in that symmetrical model, it's kind of weird, right? I've put numbers for the generations here, but if you try to spot any difference between like those 3 columns, you're not going to find any. This model has like a 3-fold symmetry. And that symmetry is broken as soon as you include the Higgs boson, right? You see, we've talked about how these particles interact with the Higgs, they acquire a mass. And that's what allows us to say these are 3 different generations. Because you'll see, okay, 2.2 MeV, 4.7 MeV, then second generation, they're more massive. It's a 1.3 giga electron volt, 96 MeV, and then the third generation, this is even more, like 173 GeV and 4.2 G. And so this generation structure is encoded in what we call Yukawa couplings, which is basically just a fancy way of saying it's a set of numbers, right? We know the mass of the quarks. We know the average value of the Higgs field in vacuum. That's like basically where the minimum is on the Mexican hat. This we know precisely. Mass of the quarks we know. And we know that the Higgs can generate this mass by interacting. But we basically just, to like connect the two, we basically just like input numbers that make the whole thing work. But we don't know where those numbers are coming from. And that's a kind of a blind spot in the model. This, is more descriptive than it is something that explains why we have this like 3-fold generation structure. This is not explained. We're really just like inputting numbers that correspond to what we see. But we have no explanation for why nature is this way. So we call this the flavor puzzle. And studying interactions of Higgs with these particles is one of the ways we can try to shed light on this problem. And that's what I'm working on. So, okay, now I'm going to look at interactions with different particles, okay, what we've measured so far. So on this axis, this is particle mass. And on this axis, this is like roughly the strength of the Higgs interaction with each particle. And you see the line here, this is the prediction in the standard model, where basically you have, as we were saying, the mass is predicted to be proportional to the strength of the interaction with the Higgs boson. And for a lot of particles, this matches very well. So on the far right, you have the top quark. In the middle, we have the bottom quark, right? Here, the muon. However, I've circled it for the charm quark. The bottom quark is a 3rd generation quark. Maybe I can just quickly flash here. You have your top and bottom, but 2nd generation charm, we don't really have a good measure for this one. We put it here because it's possible to do, but there's still a lot of ways this can go wrong, right? And so constraining this is extremely important. Like measuring this ever more precisely is very, very important. Because you could find that there's a lot of theories that predict, for instance, like that the coupling of the Higgs to charm quark will be larger than the coupling to the bottom quarks, for instance. This is not a prediction of the standard model, but there are theories that predict that. So it's important to test that. How do we do this? Okay, well, we have to reconstruct those charm quarks or those bottom quarks, depending on what you're looking at. And we do this with flavor tagging algorithms. This is a field of research we are very active in the Berkeley group. And the intuition is, okay, heavy quarks will travel a measurable distance from the interaction point before decay. So primary vertex here, this is where the collision happens. And if you have processes that happen, if like a light quark is created and if you reconstruct its trajectory, right, with, for example, with the first part of the detector serves exactly that purpose, well, it's going to point directly to the primary vertex. But if it's a bottom quark or a charm quark, these are heavier. And for a number of reasons we're not really going to get into, they will travel a measurable distance. You can actually measure the distance. If you reconstruct the trajectories well enough, you can measure the distance. And this gives you a handle on whether it's a light quark or a heavy quark. Now, of course, it's a lot more complicated than that. Nowadays, it's implemented by sophisticated AI/ML algorithms. We have a paper coming out in Nature Communications actually that's explaining this. And it's a cutting-edge transformer model. I don't know if you guys know about that. It's the same technology as like ChatGPT. We just apply it to this problem instead, and it works extremely well. So this basically enables us to, with a very high efficiency, to reconstruct either bottom quarks or charm quarks in the detector. So okay, for the coupling of Higgs to B quarks, we can just be more precise. But for the charm quark, this really enables us to zero in on the nature of the interaction of the Higgs with that particle. Of course, this is still extremely difficult because as I was saying, if the gluons can also decay to pairs of Bs, that's a signal that really looks like Higgs decaying to B, so it's very difficult. So what we do instead of looking at everything, we just zero in on like one specific process. So here, again, this axis, this is time, and this would be distance. So the fermion series would be two quarks from two protons in the beam. They're like coming together. They annihilate into a vector boson, so either a W or a Z, and then that vector boson just like radiates off a Higgs boson. So this is not the most common thing, but it's still, kind of common. But the thing is, you remember when I was talking about Higgs to ZZ, when I said our detector is really good at detecting electrons and muons, especially muons. So we take advantage of that here. For example, if we have a Z boson, we require it to decay to a pair of leptons. And this we can identify extremely efficiently. And moreover, these events where the gluon splits into a pair of Bs, this almost never comes with a muon or an electron. So when you've required that, you completely kill that. So that's what we did. And I just wanted to put like one result. We can take our time. This is a little bit of a complicated one, but to me, that was like the most important outcome of this paper. So as I was saying, there's some theories that predict that the interaction of the Higgs with the charm quark could be like on the same level or higher than that of the bottom quark, even though the bottom quark is heavier, right? So that would be a different, modification to the Higgs mechanism. So we tested that hypothesis here. So basically, we fitted a ratio here of, we measure the number of times we can see the Higgs decaying to charm quarks and the number of times we can see it decaying to a bottom quark. And we just, ask ourselves, what could the ratio be? And if, okay, this is the part where it gets a bit confusing, is the way that we've expressed it is not by looking at the coupling strength directly, but we fitted just a factor here. So if, for example, kappa C, if this is 1, this means that we don't modify the standard model prediction. That would mean, and in fact, okay, this is a negative log likelihood plot. So at its minimum, this is the most likely value. And you can't, probably from where you're standing, you can't really see it. But it sort of goes up here, and then the minimum is at 1. So that's still the most likely value. But then, here you have, for example, a 68% confidence level. So you're confident that, 68% of the time, the real value will be like within here. Now, if the coupling to charm quarks is equal to the coupling to B quarks, then we need to modify either the coupling to B or the coupling, we need to make the coupling to B smaller or the coupling to charm larger, right, than the prediction. So we need to change that ratio. And since these things in the standard model, the prediction is correlated to mass, then we need to set the ratio at the ratio of the masses. So this is why if those interaction strengths were the same for charm or bottom, you would get a value that's like 4 point something, because that's the ratio of the masses of the bottom and charm. But you can see all the way to the top, the number on that topmost dashed line is 99.7% confidence level. And you see that like it's like right where that line is. So at that confidence level, we're pretty sure that we can exclude this, right? Because the higher you are, the less likely, the more disfavored it is by data. So,
I just start.
yeah, go.
So the green line is what you would get if this alternate
Yes.
version of the theory is true?
If the interactions of the Higgs boson with the chunk quark was at the same strength as that with the Higgs boson, you would measure something that's right.
Got it.
But you see, as I said, if the most likely value is at the minimum of this function here, which would be here, and if this value here is like right at the edge of my 99.7% confidence level, this corresponds to what, in sigmas, at 3 sigma, we're able to say that this is not the case. The coupling of the Higgs to the chunk quark has to be smaller than the coupling of the Higgs to the bottom quark. At 3 sigma, that's what we've established with this analysis. So this can exclude a bunch of theories that tell you that the interaction with the charm would be higher than that of the bottom. So it's an important milestone. And yeah, so this only scratches the surface of all the research that we do at the LHC on Higgs. There's a lot of opportunities if you guys are interested. We always have many Europe students. There's also the SULI program at Berkeley Lab. We constantly have undergrads that come work with us at the lab, and also grad students are always welcome to do rotations. And yeah, there's a nice article in Nature, the Higgs boson turns tan, which came out a few years ago. If you guys are interested in learning more, I highly suggest reading that. Okay. You guys have more questions?
Thank you so much. We have a lot of questions.
Yeah. Which group do you work with, like within the ATLAS collaborations, or which advisor, which professor?
Yeah, I work with the Heather Gray. But yeah, the ATLAS group here isn't common with the Berkeley Lab group. So my office is actually at the lab. Like I have an office here, but I'm never here. So I'm mostly at the lab. Which is why, yeah, if you guys, Europe is, of course, this is true campus, but there's also SULI that not everyone knows about. But that's also a nice program that's like Berkeley Lab specific.
What is the day-to-day of your research about?
Yeah, I mean, it's a lot of like being in front of the computer like
Yeah.
this, crunching data. I lived in Geneva for 2 years. I was based there. And I also was mostly on the computer, but there I also worked in the control room of the experiment. So I was shift leader for a while. It's also always fun. The first time you're like managing the whole operation for like 8-hour shift. And the first time this happened, the first time I did it, okay, everything was going fine for like the first hour. It's like 7 a.m, drinking my coffee. And then alarms start going off and like the 2 huge magnets were just like completely lost power. Yeah, it was a huge mess. I was like on the phone for hours, like just calling every expert, like, please come. Yeah, it was a good experience. But yeah, the day-to-day is mostly like I prefer. It's a bit less stressful being in front of the computer and we're just like analyzing the data, coming up with new ways to analyze the data, writing papers and so on.
So you don't really work with the CERN, like the machine itself?
Yeah, I personally don't, but at the lab, we have 2 labs, basically. In 2030, we're gonna replace a part of the detector. And we have 2 labs that are building like parts of this upgrade. So there's a lot, like if you guys are more interested in that, there's a lot of opportunities like through these 2 programs to actually actually build detectors. I'm more of a software person. But
Is there a difference between the nature of the projects that offer at Europe and at SULI?
I don't think, like in practice, I don't think so. Like in theory, probably like the kinds of application you're gonna make for Europe and SULI is gonna be slightly different. But at the end of the day, you'll work with the same people on the same projects.
You do know that with SULI, you don't necessarily know where you're going to get placed you can apply to various groups, but.
Yeah, you might not,
Yeah.
it's like Berkeley lab wide.
Yeah.
But they also, yeah, there's the physics program at Berkeley lab is also not just ATLAS. It's very wide. There's like dark matter experiments, there's neutrino experiments, there's nuclear physics, there's a lot. There's really a lot. Yes.
For these big machine learning models that you have to use to analyze.
Yes.
Complicated data, what are all the different inputs for that?
Yeah, it's kind of simple. You have these particles that come through the detector. Maybe I have to just skip back quickly to this picture. Well, bear with me. The particles are like flying out, right? And they pass through this detector here, and we just sample their position at like different layers. And this is one of the things I work on, like algorithms to reconstruct the trajectory of particles. And this is basically just what we input to the algorithms. We're like, here's where did the particle pass. And we know if it's, if it's an electron, right? Because it'll stop here. You know if it's a hadron, because it's gonna be there. Usually you care, like if you care about like B quarks, they're gonna die in this hadronic calorimeter here. And you see this creates like a lot of junk, but also a lot of particles that you can trace. So we just reconstruct all those trajectories, we input that to the algorithm, and it's exactly, the intuition is still right, even though nowadays it's more complicated than that. But you can get like very, very far by you reconstruct the trajectories, and then by combining trajectories together, you can build like vertices, like interaction vertices, where you know that, okay, my B quark traveled this far, and then at the top, you see that it also decayed to other particles, because it's a fairly heavy particle, so it's not stable. So if I reconstruct the tracks from these particles, I can say, okay, they decayed at that point, which is far from my primary vertex. And you can get very, very far just with that. And for a long time, that's how this was done. And, fairly recently, I mean, we were using, I don't know, you guys maybe don't know, like boosted decision trees, which are like machine learning models that are not neural networks. They're less sophisticated, but they were like very popular when I started, working in ATLAS in 2015. And but now, yeah, every time there's advances in machine learning, of course, we jump on the bandwagon. And so far, this has served us well because, when I started working on like Higgs to C, a lot of people were skeptical. They didn't think we could do it because, okay, this scheme works fairly well for B quarks, but C quarks will travel like much less further before they decay. So it's like a lot harder to do. And before like this revolution with like new machine learning models, people just flatly didn't think we could do it. And then we did it. And, we had like spokesperson of the collaboration saying, oh, wow, you've proved to us that we can do Higgs charm. That was great. But yeah, it's really it's not like just the work of people analyzing the data. It's also coming up with these crazy, these very fancy, crazy algorithms.
How much do you have to think about how interpretable, physically interpretable the models are?
We try. It's on the best effort basis. But basically, we always calibrate these things, right? So we have like other means of identifying like B jets or C jets. They're just like way, way less efficient. But some of them, are kind of simple in nature. So you can do them in simulation, you do them in data. And these are like, the simpler the method, the more interpretable it is. So you can like convince yourself that it does the right thing. And then we compare this to what we see with this algorithm, and then we just correct it so that it's not biased, right? This is a bit of a problem, right? Because usually you train this thing and you look at its performance and it's great, and then you calibrate it and the performance is like a little bit less. So that's a very active field of research. Like, how can we train these things so that they don't get biased when we apply them to the real collision data? Because, yeah, maybe I should mention this. We are only training this on simulation, right? Which is like, the simulation is not like a toy simulation. It's based on like quantum field theory and so on, like our best knowledge of interaction of particles with matter, but it's still not perfect. So once you've trained on this simulation, when you've applied it to actual data we're getting on a detector, it's always going to be a little bit different, but we correct for that so that it's not biased. So we do at least that. So we're confident that it's not wrong. But insofar as understanding exactly what happens, this is very, very difficult. Yeah, there's people that do work on this, but there's nothing that I found very straightforward to interpret that came out of it yet. But one thing's for sure, we know that the better we can have a resolution on the positions of these things, the better these algorithms function. So we're also confident that this is a big part of it.
Okay.
Yeah, let's go ahead.
The Mexican diagram, you find out that Higgs boson has a particular mass, but there's another free parameter, which is the direction. So what happens if the direction changes?
Yeah, this is a little bit, you mean like around the, yeah. So, okay. How can I explain this in a way that's both correct and not both less encrypted? Basically, okay. The mathematical model we have here is it's expressed with a Lagrangian. Do you guys know what that is? Like, or a Hamiltonian, it's the same thing. So we write this, but if you in the world as we want it to be, it's like built around these symmetries I was talking about. But if instead we expand this Lagrangian here, around the minimum, you'll find that excitation around the trough correspond to, they're just one component of the massive double boson. Because in the world where we don't have mass, you don't actually have a W boson. You have, I think, AB, B1 and B2 bosons. And if you do an expansion of your Lagrangian around the trough, they kind of mix together with this extra mode to create a massive W boson. So it's not a real particle, it's a component of particle, for lack of a better term. This is probably not super clear, but I think there's no great way to explain this without really diving into the math. But yeah, in theory, this was a problem for a long time because excitations along the trough, these are known as Goldstone bosons, which don't have mass. And so if they existed, we would have found them. But of course, this is not like in the real world, we don't have two different kinds of photons. So this clearly doesn't work, but this is the, just a component of another particle.
Then if the gravity were to have another universe where the ground state is in a different direction, would the physics be the same?
Well, if it's around this trough, yes. But there's one very, very neat thing, is that the exact shape of this potential, we don't know it super precisely. The only thing we know precisely is where the minimum is. So as long as whichever phase you pick, when you quantize the theory, it doesn't really matter, but the shape of the potential can matter in the sense that, okay, here, this suggests that the potential just grows, right, as you move away. But we don't know it precisely enough to say that. It might rise and then fall. That's unconstrained, right? And then, of course, if you pick a ground state that's away from this one, then yeah, then the physics is completely different. The masses of the particle everything will be off. And so this is a problem called the metastability of the universe, which means that if there's a big enough fluctuation in the Higgs field, which actually pushes us over that bump, if it exists, the universe will just be destroyed at once. So yeah, no. I hope this won't keep you up at night. We don't know if this can happen, but there's also, I've seen presentations where people were talking what if the potential would have a little dip at 0. This is also allowed given our knowledge of this thing. And some people say, what if far in the future we can learn to control the Higgs field and create pockets of space-time where the Higgs field is 0? Then you will likely have a very different kind of chemistry So there may be like technological applications of that, but this is still sci-fi. But yeah, I think, you know, if you're staying in that trough, you're probably the equations are symmetrical with respect to the exact phase that you pick. So it doesn't matter. And it's even more than that, right? This is what we call a gauge symmetry. The model is built around what we call local gauge symmetry, which means that the minimum you pick around the trough, it can be different depending on like where you are in space-time. It doesn't have to be the same. And this has like far-reaching consequences. Like, for example, okay, this works the exact same way for quantum electrodynamics. So if you have like a free electron, right, you have a wave function that, have you guys done quantum mechanics at all? So you know what a wave function is? It basically tells us, yeah, the probability of measuring an electron at some point in space. Okay, so it's a wave, right? And you can pick the phase, like the initial phase of that wave, and then do all your calculations. They come out the same way, whatever phase you pick. So this is a global gauge symmetry. But the local gauge symmetry is saying like, okay, I want to be able to change the phase that I picked everywhere that I am in space-time. So now the phase depends on where you are in space. And so, of course, now if you're taking like derivatives, you get a different answer because it also depends on the variable you're differentiating with respect to. So the only way to make this work is to introduce a second field that under that, you know, local phase transformation transform in exactly the right way to cancel out this difference. And when you do this for the electron, it turns out that this field you introduce is 100% consistent with photon. So you have an electron, you have local gauge symmetry, then you know you cannot avoid having a photon. And you follow basically the exact same scheme, you get the rest of the model with a lot of intermediate steps. This is the idea. Hopefully that's not too cryptic. Do you have other questions?
So that will be the lecture for today.
Thank you.
So please, before we leave, please take a moment to sign help us to keep the lecture running. And please, thank you to all the speakers.
Thank you for coming.
Thank you.